transport processes, and you are doing it from your undergraduate actually. So transport processes are made up of 3 type of processes, and we are studying them all together under a single framework here. I understand some of you might still be in the surprise quiz, but please try to be here. Right? So let me ask you a question that another question that have you encountered a temperature profile, concentration profile? You must have drawn at some point for some exam, right? At least a heat transfer within a slab, it's a flat line. All of you must have drawn it, right? It's like this line. If it's non-linear, then you get, if it's a heat generation within a slab, you get something like this, right? If it's linear, you get this, or you get that. You never get breaks. Or you never get profiles like, there's never a break, right? Unless there is a boundary. Unless there is some interfacial boundary condition. Let's not go there. But I'm just saying, if there is single continuum phase or continuous phase of, let's say, any liquid through which you are studying mass transfer, any slab through which you are studying heat transfer, these temperature, velocity, concentration profiles, they are always continuous, right? Yes or no? There are no empty spaces in between. There are no jumps in between. Why? Why is that? Because we make an approximation under which we are doing all these things. That approximation I want to start today. Any guesses what that could be? Continuum hypothesis, right? So there's a fine line between approximation, assumption versus hypothesis. Hypothesis is an assumption based on sound scientific rationale. And in your course and in science in general, people, when they say this is this approximation, generally they mean hypothesis. Based on a justification, they are assuming something. So we'll talk about continuum hypothesis today. And focusing, we'll be completely focusing on fluids, which is liquids and gases. Okay, and this idea of continua, as it was called before, is not new. It is from the time of Aristotle, who said that this world is made of water, sea, air, land. Each of these distinct quantities, they don't have any empty spaces. What he means by that, water is water, there is no empty space within water. It's a continuum. Air is air, there is no empty space within air. It's a continuum. Yes? But is that true? Now that we know molecules exist, right? Atoms exist. There is empty space in between. It's just that it's not visible to us. Yes? So, and I have uploaded a video. So please take out your mobile phones. You see that? It's a short video. It doesn't go again in loops. But what you see there is a fluid simulation zoomed in a very small scale, in which you see molecules jiggling around. You see that? Anyone not able to see? So that is a simulation for 1 picosecond. So it might seem to you that it's very slow, but it's just not. I don't want to even say fraction of seconds. It's several fractions of seconds. So if you saw it in real time, in that same space, it would seem very violent. Yes or no? So you can clearly see that there are empty spaces. Now that everyone knows what molecular simulations are, why isn't world doing molecular simulation? Why do we still have CFD solvers, COMSOL, ANSYS? Why do we do all that? So how many of you have heard molecular simulations before? Many of you have heard. It's what is essentially about. It is just basically Newton's law. F is equal to ma. You apply F is equal to ma at a bunch of molecules together. So you say in this small chamber there are these molecules. Each of them will be governed by F equals to ma. What that F will be, it's a sum of forces. right? If you have a small molecular component, it will have Brownian forces, right? So one could write a simple equation. Mass times acceleration could be written as mass times d square x by dt square. And since you have multiple molecules, so you will index them. You will say molecule number 1, 2, 3, and so on. So each molecule will obey this. This will be equal to sum of all the forces. So you could write the Brownian force plus the collision force. And this collision force could be written as sum of all the collisions. So J equals 1 to n. J should not be equal to I because something cannot collide with itself, right? Into F, some interaction or collision with respect to J. This is the, in a sense, crude way of looking at a molecular dynamic simulation. I'm sure there are other things involved, but essentially it comes down to writing simple laws of mechanics for molecules. Why don't we do this? When we are simulating, let's say, this water in a glass and I shake it and it will move, why can't I do a molecular dynamic simulation of this entire glass? Some of you have heard of molecular dynamics, right, before? No answer. Because it's very expensive. How many of you have done molecular dynamics? What volume did you do it for? What was the problem you were looking at? What was the problem? If you can disclose it, I mean, otherwise. You are doing DFT, right?
I just started the course. It's just based on a single atom or a single crystal structure in itself.
What's the size?
I think picometers.
Picometers. Sometimes nanometers. At max, you can do several nanometers, 100 nanometers maybe. But you can't go beyond that. Certainly not few centimeters. Why? Because you have so many molecules to account for. So you have to write this equation for many, I mean, I don't know how many, 10 to the power 3, how many moles are there that you have to multiply with 10 to the power 3. So many molecules to account for. So it is completely impracticable. I mean, it's not practical to do molecular dynamics for large scale flows. That's why we still do continuum approximation. And it works really well. It's really pragmatic. Okay. Although it's, so now what I'm getting at is that although it's not true, although it's a false assumption that we make, but it works. Okay, but there it's not like that it works, it doesn't have challenges associated with it. There are two main challenges that I'll talk about. But first let me tell you when can you make such approximation and when you cannot. For example, when you're looking at picometers or nanometers, I mean picometers is really small, but when you're looking at nanometers, why continuum approximation might fail. Right. So imagine that this is your window of observation and you have some entities. And I'm not telling you that this is, right now just imagine that this is some length scale. This could be kilometers also. I'm not telling you that, and we may be looking at planetary scales. So don't think about, don't confine yourself to small scales. I'm talking in general. There is a box in which you are seeing entities. This could be small particles. This could be people in a crowd, or these could be some intergalactic stuff. And there is a length scale between the molecules. So they are moving around, but eventually they'll collide. So this is something known as the mean free path, meaning the average distance they travel before colliding with each other. Okay, and then there is length scale of this observation. If you want to make a continuum approximation here, you have to ensure that this mean free path should be much smaller than the length scale of observation. Because if not, then you will be taking into account individual particles. Now, coming back to the water case, if you were looking at a glass of nanometer size, some small volume of water near to a surface, and you wanted to look at the water molecules, your window of observation is too zoomed in to assume it to be continuous, because there are empty spaces. You have violated the very definition of continuum. Yes or no? If you take this ratio, This would be called, if you take this to the other side, something known as Knudsen number. So it essentially tells you that when you make a continuum approximation, you're saying that this is my invisible length scale. I will not be able to comment on whatever happens on the collision scale. That's invisible to me. All I'll see is the large scale macroscopic picture. Yes? So this you can already decipher, right? This is already comparable. So this would be a continuum if I add 100 more particles here. Then you could start to classify it as a continuum and so on. Okay, we get some gist of, I'll touch upon another example for water again, but just want to approach it from a material point framework. So let's say you can understand that, okay, fine, I understand what is continuum. You are zooming in, zooming out of a problem so that crowd appears like a fluid, right? As you go on in an aeroplane and you see a heavy traffic jam, you can assume it like a bunch of particles going together, and you can model it as a continuous stream. So you get the idea. But whenever we write, for example, whenever I give an example of heat transfer through slab, right, and you had this profile, and you say the temperature here at this, let's say at x equals to 0.5, time equals to 1 is equal to something. What do you mean by this? Temperature at this time and this space. What does it mean? So this is a continuum temperature. This is a zoomed out picture. Yes? Let me write a question clearly. What do we mean by f x comma y comma z comma t? F could be temperature, concentration, pressure, velocity, whatever, density. This we call as material point. In short, it is, this point is some average of this. Since you've zoomed out, right? So let's say you zoom in and then you see these small particles, but if you zoom out, you see a continuous stream, and then you say this point. That point has lots of small elements, but you're ensuring that you obey this. The length scale of that material point that you've chosen is much smaller than the collision scale. Let me give you another example, more classical example that you might have heard of. And in the context of water, let's say this quantity F I'm talking about is density. And let's talk about this room, and I pick a point in space, this point. How would I measure up? I mean, and let it be as the size of this glass. How would I measure the density of the air contained in this glass? Let's say I have a device. How do you measure density? Volume you can find out. Mass, let's say you can measure. You'll get some number, whatever density of it is. Now, and you start plotting it. So this is density, and this is your scale of observation ka volume. The volume of scale of observation. Yes or no? So if you want to see, this could, you can write it as L cube, meaning you took a cube of something like this, L. Okay, and you are here, and I told you, okay, fine, reduce the size to half. So your times, this became 8 times smaller. I mean, reduce the size of your observation. Will you find the same density? So it was quite big, right? You reduce it to half, you find the same density, and if you keep going on, you will get a straight line. Yes, indeed. So you'll approach 1 micrometer, you'll still get the same line. Somewhere around few nanometers, you'll see fluctuations. right? I mean, after all this picture, it must be clear. You will see fluctuation because your observation scale will detect voids, and you already saw those violent. I mean, they were slowed down, but in a span of second, it will be very violent, right? So at some point when you observe, so let's say same experiment here you do, and you see, oh, there is no molecule there, or maybe two molecules are there, so density is less. Next time you do, they are crowded. So here that experiment would fail, yes or no? This experiment is nothing but the continuum hypothesis, the thought experiment. All right. So this is the picture that this is the scale that we draw, and classical fluid mechanics books write that 1 micrometer is a good enough approximation for this continuum length scale. That when we are pointing something, we are saying that we are looking at a small volume of 1 micrometer cube. That is your material point. And when we say temperature, say the temperature at this point, we are actually saying that it is the volume average temperature. Sorry, the volume average temperature of the entire cube. So you have molecules there, you're doing a molecular average, volume average. Okay. I mean, in the same way, when you say velocity at a point, we are doing a velocity average. Any questions? So typical textbooks give you 1 micrometer, but safely one can make continuum approximation until 100 nanometers, 100 to 50 nanometers even. I have published research papers in which I have assumed something called electrical double layer, which can go as less as 10 nanometers, and it's widely accepted that you can make those approximations. But if you go below 10 nanometers or below 1 nanometer, then your problems start to emerge, right? Because water molecule is how big? Few angstroms. So you need to at least be 10 or 100 times larger. Your observation space should be that big. Comes roughly about a nanometer. Even you want to ensure 10 nanometers. Okay. If you are not working with water, if you are working with large scale macromolecules, polymers, do you think that your criteria for L would change? Your criteria for, or the point where this continuum hypothesis will fail will shift, because you're increasing the size of your people, your folks. If you're talking about bacteria, which are tens of micrometer of size, then your L would shift, right? So again, these are continuum approximations. There are models for crowds, for large scale bodies, but then you have to be aware of what is the limit of your approximation. Okay, so this is the general rant about continuum approximation and its limits, but there are two challenges still. So let's say we are very 10 nanometers ke upar we are observing everything, but still there are some challenges here. Anyone wants to point out? For example, the quiz that we did just now, surprise quiz, you have a problem of flow through a pipe. You have solved flow through a pipe problem before? Pressure driven flow, shear flow, Couette flow, all these things you have heard, right? You solve Navier-Stokes equation, or you do shell balance, whatever. What happens at the edge of the boundary? So let's say you want to solve this problem and you want to get this famous profile, right? In order to get this profile, you have to apply what? Navier-Stokes equation. But at the boundaries, can you apply Navier-Stokes equation? No, because that is for the domain. For boundary, we have the boundary conditions. So the continuum approximation only works for the domain in which there is fluid. Boundary pe there is boundary. So continuum approximation will not tell you that, oh, the fluid, what is the propensity or the tendency of fluid particles? Are they going to slip? Are they going to no slip? Right? So that is your responsibility to provide the model or to take care of this issue. We'll come to that. But this is something that continuum approximation cannot help, because it doesn't lie in the domain. Point number 2, challenge number 2 is the following, that we know the true picture is the molecular picture, but we are looking high above. We are looking at a zoomed out picture. So what will be? So I mean, if there is a fluid flow and I move my hand like this, fluid, some layers above will feel it. We all know it's viscosity, but let's pretend we don't know. There is something happening between them, right? How to capture that? That's a challenge. Although you have already overcome and someone told you ki, Newton's law of viscosity hai. But you can see now that it's a challenge. That you know that Newton's law of motion governs the individual molecular motion. But when you zoom out, you can't apply that Brownian force, collision force, because you're not even accounting for it. So what will you apply? So you have things like viscosity, things like diffusion coefficient, things like conductivity, which actually do not exist if you look at the molecules. Right? What is, if you're looking at a molecule, what is viscosity? Nothing. It's just collision. So how do we go from micro to macro is another challenge that we have with continuum approximation. I mean, it's still a challenge when you're looking at complex fluids. You know this stream of research called complex fluids? In industrial scales, we don't have Newtonian fluids generally. We have some polymers and so on. So this question is still there. We have these complex polymers का एक slurry बना हुआ है. How do we write a constitutive equation for this? How do we go from polymeric interaction at the small scale? How do we account that? Right? So that's challenge number 2. Okay, but there is something very positive once you overcome these challenges. For example, in your question that you solved today, you know what relation you were trying to derive? Hagen-Poiseuille law, right? I mean, although for that coefficient you need to do the entire analysis, but at least the scaling you must have got. So Hagen-Poiseuille law is, once you solve this profile, you get that. So at the end of the continuum approximation and the hurdles, and if you can do analytical calculation, there are these cute formulas that you can derive and tell other people, and people can handily use it. 6 pi mu a is the drag force on the sphere. Easily you can use, right? So this elegance and this ease lies if you overcome this hurdle. Okay. Before we move on to the technical aspects, the maths, one final point. One expert here may ask me, so I'll ask it myself. Is that fine? I understand the continuum approximation. If there is a fluid flow, I put a point. What is that point? That point is the average. But what if I have fluid flow, on top of that I add some solute? Now there are two continuums interacting with each other, right? Yes or no? This aspect becomes a bit tricky to define. Even one of the most famous books, sort of, we are very cautious about it. And this is known as the interpenetrating continuum. Basically, in which you assume is that if this is your length scale in which you have zoomed out, and so let's say you put a point and say, tell me what's happening in this. So you'll have fluid molecules interpenetrated with the solute molecules, and this is your material point. So the two continuas have interpenetrated. You don't have to worry about anything. You'll still solve the same equations. I'm just telling you that when you solve the convection diffusion equation, as some of you may have solved it, you are in this framework. Yes? Okay. All right. So we'll begin with the calculus of transport phenomena. Okay. And which calculus should we talk about? Many types of calculus are there. Eventually we have to cover everything. But it should not become Math 101 course, right? CHE 611. So we'll do a crash course. Okay. But let me tell you which one to cover first. So, for example, what in any transport process, it's an out of equilibrium process. Um, it's governed by temperature gradient. So you have temperature variation in space, 3D, yeah, and then pressure variation in time. So you have gradients and you have rate. What sort of calculus brings them together? Rate of change of temperature, let's say, and gradients of temperature, spread of temperature, slope of temperature. What? Some differential equation. And if this is there and this is there, dou t by dou x or dou square t by dou x square, they have to be somewhat in one equation. Then which calculus does it become? Differential calculus. So you have to study this, how to solve such equations. But there is another one. How do you get these equations? That's a major part of this course. Usually you would do shell balance, right? But we won't do it here because it's limited in capacity. What are the limitations of shell balance? Transport phenomena, many of you did, right? What are the limitations? Does it work for complex vertical flows, or does it only work for laminar flows? In BSL we start, right? So for greater generality, we will derive these equations not from shell balance but from integral balance. So you have integral calculus. So first we will do this, then we'll do that. But before integral calculus, we have to do another calculus because we'll deal with vectors. Velocity is a vector. Gradient of temperature is also a vector because it has a direction, right? Where is the temperature decreasing? Where is it increasing? So we'll do vector calculus.